So by now you should be comfortable with the idea of energy bands in solids, and depending on which material you are talking and what kind of electronic configuration is there, the crystal parameters, crystal structures, all those things, you have three broad categories of energy bands. One in which you have filled bands, filled bands, filled bands. The highest filled band, which we called valence band, and then you have next is conduction band, which is not completely filled. It can be completely empty or it can be partially filled. So one variety is where it is partially filled. You have a large number of quantum states which are filled, and you also have large number of quantum states which are empty. So this kind of conduction band, and this we said that this will be electrically conducting. So it is in the category of conductor. So this is one variety. Metals fall under this category. Then the other variety is that the conduction band is completely empty. So valence band is here, and then the conduction band is completely empty, and this gap, this energy gap between this valence band and conduction band is much larger than K into T. So normally we work at around room temperature, and at room temperature this K into T, as I told earlier, this is 26 milli-electron volt or 0.026 eV. Right? This K is Boltzmann constant. Boltzmann constant K, and then this is the temperature in absolute scale. This is temperature in Kelvin, and that is this. So as compared to this, if this gap is very large, then that is one category, and this very large, I said that let us say Eg is greater than some 3 eV or so, you can take that as large, 3 eV, 4 eV, 5 eV and so on. So this is one category, and this will be insulator. When I say completely filled, completely empty, remember this is for the very low temperatures, close to 0 K. Once you are at room temperature, and if this Eg, then this Eg will decide whether some of these electrons can be promoted here, because in interactions this thermal energy exchange takes place, and that is of the order of kT on the average. But then there are interactions where the energy exchange is much larger than this, 10 times this, 50 times this, 20 times this. There are interactions in which the energy exchange is much smaller than this. So the average is this, but you do have some events in which a thermal energy can be much larger than this. But if this gap is very large, if this gap is very 100 times of kT, that will be 2.6 eV, 100 times, 200 times, 300 times. Then even at room temperature, through thermal interactions, there is a negligible chance that some electrons will be accepting those thermal energies and going to this conduction band, and therefore it still remains empty. And these are insulators. Why this is conductor and this is insulator? Because when you try to pass current through the material, you essentially apply an electric field by whatever connecting battery or so. And once you apply electric field, that electric field tries to give kinetic energy to these electrons. Now these electrons are not going to accept that, these electrons are not going to accept all that, these are going to accept that energy, and since the quantum states are available, That is why they respond and they move according to that electric field, and you have conduction. Here you do not have electrons here, and therefore electric field cannot do anything to these electrons because there are no nearby empty quantum states. So these electrons will just refuse that energy from electric field. So this is insulator. And the third category which I am interested in this course mostly is where the structure is of this type. The structure is of this type. At low temperature this is completely filled and this is completely empty. Conduction band is completely empty, but then this Eg is not very large as compared to K into T, and this variety we say it is semiconductor. This is because at working temperature, at room temperature or temperature in which we generally do all our work, at that temperature, if this Eg is not very large, then through thermal interactions, some of these quantum states may become empty, the electrons going to this and populating these quantum states. So we have empty states here, empty states here, empty states here. We generally call it hole. Okay, so you do have some conduction electrons in the conduction band. And remember, there are too many large number of empty quantum states. So if you apply an electric field, these electrons will respond just like these electrons. So these conduction electrons, now there are some conduction electrons, some sizable number of conduction electrons, although it's much less than the case of the good conductors, but some conduction will be there. And also, since now there are some quantum states here which are empty, electrons have gone, and therefore if you apply an electric field and if you have an electron here, if this quantum state is filled, electron is here. But then in this neighborhood you also have an empty quantum state because electron has already gone there, and therefore an electric field is there. Once the electric field here is there, it is on the entire material. Entire material means this electron will also feel that electric field, and if there is a empty quantum state here, then this electron can accept energy from the electric field and go here, and that will also constitute a current in the material. Electron responding to electric field and moving according to that electric field in the direction opposite to that electric field, that constitutes a current. A systematic drift, a systematic movement of electrons in response to electric field, that constitutes current. So here also this electron can go here, and if this electron can go here, if this jumps here, this quantum state becomes empty, and then some other electron can accept energy and go there, and so on. So in a semiconductor, the current is composed of two parts. One is because of the conduction electron and one is because of the holes. We call these empty states as holes, right? So you have two kinds of currents. One is these conduction electrons which are responding to the electric field, and one are these valence electrons, electrons in the valence band. These are the electrons which are not that free to move in the entire crystal, but then even in their localized domain they can make some current which you can say it is IH. Here it is not the case. Here these electrons are in large numbers, and therefore even if some holes are there, it's almost negligible. So this is the kind of conduction mechanism which is there in semiconductors. Now this has a profound effect on the temperature dependence of resistivity or conductivity. You must have known this formula, that resistance of a wire, let's say you have a wire, a metallic wire, copper wire for example, or aluminum wire, or any conducting wire, tungsten wire. In the filament bulbs which are now gradually fading away, going away from out from this world because of these LEDs and all those things. That is also a semiconductor evolution. So if you have a copper, aluminium or nichrome wire or tungsten wire, which are good conductors, okay, which are good conductors, and you raise the temperature, then the resistance at some temperature T is equal to resistance at some other temperature, lower temperature. This is if you heat, then this becomes 1 plus alpha times T minus T naught. Correct? You must be knowing this equation. This alpha is known as temperature coefficient of resistivity. Once you increase the temperature, then the resistance goes up. And in elementary classes, we say that, okay, now the electrons are making more collisions with the whatever they encounter in the lattice, and because of this increased number of collisions, they are not able to go ahead in response to the electric field, and that is why you have all these resistance increasing there. But if you talk of semiconductors, increasing temperature is a big asset, because these conduction electrons which are here, these quantum states which are filled, they are because of the temperature, they are because of this kT. If the temperature is more, then kT is more, and then this Eg of the order of or slightly more than, not very large than kT, that is satisfied even better. So if you have this 26 milli electron volt, in place of that, if it becomes 30 milli electron volts, so the energies which are made available to these electrons is now more, and therefore more number of electrons can jump here, and therefore the number of conduction electrons and number of holes both can increase, and if they increase, the conductivity will go up, the resistance will go down, because you will have more current. So for semiconductors, resistance decreases as temperature is increased. Okay, opposite to what a conductor will do. For a conductor, resistance increases as temperature is increased. This can be used to identify experimentally which material is conductor and which material is semiconductor, or if in some process there is a transition, from metal to semiconductor or metal to insulator, going towards insulator. So if there is some kind of transition, that transition can be identified experimentally by looking at the temperature dependence of this resistivity, and you can identify when it was in that conducting era, conducting zone, and when it becomes in this semiconducting or insulating zone. So now let me talk of the model semiconductor that I will be using in this course for discussion, and which is being used by the entire community in semiconductor electronics extensively. You must have heard of Silicon Valley. So this entire state is named as Silicon Valley because a lot of computer work, manufacturing work is being done there, and that uses silicon. Now silicon is a very interesting material. We live on Earth and on the crust. So in that crust where we build all our buildings and everything is there, mountains, everything is there. Even if we go for mining, how much? Few kilometers, 1-2 kilometers, it's all crust. So in that crust, which is that solid part, rocky part, most of it is some form of silicon. most of it is some kind of a silicate. 80% of the crust is made of silicates, varieties of silicates. Silicates is like SiO4 is that part which is called silicate, and then there are various complexes, metals, all those things can be here. So you have calcium silicate and magnesium silicate and calcium magnesium silicate, potassium, etc., etc. So a lot of our crust is made of varieties of silicates. Then we also have a huge amount of silica. Okay, silica is SiO2. So this is also large amount, say 15% of our crust would be perhaps this silicon dioxide or silica. Sand, okay, I have a sand here. So this sand, right, this sand is mostly silicon dioxide, silica. This sand is kept in this glass vessel. This glass vessel itself is silica, most of it is silica with some kind of other materials in it. When I take this glass tumbler and drink water, actually I am holding most of silicon dioxide. The window pane glasses or the looking mirrors, we have this polish here, but then the glass here is generally silicon dioxide with some things added to make various qualities and properties of the glass. So silicon is abundant. Silicon is abundant, and it's very interesting that this silicon itself has a extremely good semiconducting properties, which has become at the center of our modern life. Silicon is at the center of our modern life. The kind of electronics that we are using every moment is based on that silicon. Okay, so silicon is Z equal to 14, and this electronic configuration will be 1s2, 2s2, p6, so 2 to 4 and then 10 and 4. So 3s2 and 3p2. So if you have a single silicon atom or capital N atoms but not interacting with each other, widely separated from each other like in a vapor, then you will have these energy levels. You will have 1s, you will have 2s, you will have 2p, then you will have 3s, and you will have 3p. And here you will have 2n quantum states, 2n quantum states, 6n quantum states. These are all full. 3s, 2n quantum states, this is also full. And here you have 6n states, and only 2n will be filled. So this is how this structure will look like, occupancy of these quantum states will look like. But then when you bring them closer and these electron clouds will start overlapping, you have silicon here, you have silicon here, and you have some kind of clouds, S and P and all those things will be there, and then they start overlapping, interacting with each other, then they will spread in bands. So they will spread in bands, all right. These are hardly they will broaden because they are inner ones. We are mainly concerned with this 3s and 3p. So 3s and 3p, if you have 3p, let's draw once again. This is 3s and this is 3p. And this broadens. This broadens. This also broadens. Okay. And then the overlap, once the overlap starts, then there is another thing, another new thing appears, which people called sp3 hybridization. You have s electrons, you have p electrons. S electrons, you know, they have spherical, spherically symmetric wave functions, and p electrons, they have two lobes type wave functions. But then when the silicon atoms come close, several silicon atoms come close and their electron clouds start overlapping, then these S states, S quantum states and P quantum states, they get mixed up. So you construct linear combinations of these S wave functions and P wave functions. A total of 8 n quantum states are there, and you again get 8 n independent quantum states, but then these, the wave function of these sp3 states will be very different from S states and P states, right. So this is known as sp3 these orbitals, sp3 orbitals or sp3 hybridization. So what happens is that if you have this silicon thing, then the minimum energy will occur, not if the electrons occupy 2n electrons here and 2n electrons here. At this separation at which the crystal forms, at that separation this will be more energy. If you have these 2n electrons in S type wave functions and 2n electrons in this P type. But if they choose to go into that sp3 type of wave functions, and for them the lowest one are filled as usual, then the energy is minimum. So that is called hybridization. So this is a schematic representation of bonding in silicon. Assume that this is your silicon atom here, this is silicon atom here, and these two are bonded, and then similarly it's bonded to this one, this one, this one. So each silicon atom is bonded to 4 other silicon atoms, and it makes some kind of a tetrahedral geometry. This angle is 109 degree between any two directions, the angle is 109 degrees. So this kind of geometry. So this has 4 sp3 electrons. And how are those sp3 electrons distributed? One sp3 electron, its wave function will be directed towards this one. Another sp3 electron, the wave function will be directed towards this one, towards this one, towards this one. So this is how the 4 will be distributed. If it is S, it is spherical. If it is P, it is 2 lobes. But this is not S, this is not P, this is sp3. So one electron is going like this, the wave function is like this. One electron, the wave function is like this, one is like this, and one is like this. But then similarly, for this silicon, this also has 4 sp3 electron. So one will be towards this one, and then the rest 3 will be towards the other 3 to which it is bonded. Similarly here, one sp3 electron will be towards this and other will be towards the other 3. So if I look for these two, one sp3 electron from here and one sp3 electron from here, they form this bond known as covalent bond. You know, people also say that this shares one electron, this shares this one electron, a bond is formed. So this is how the covalent bond is formed. So now the band structure will also be different. As you reduce the separation, average separation between the atoms, this first broadens, gets mixed up. Now here you don't have any separation, but this is not the right separation. You can take lattice parameter A as the measure of average separation between consecutive or neighbor silicons. So if large separation, It's vapor, non-interacting, it is 3s 3p. Then here this is 3s band, this is 3p band, broadened but still 3s 3p. After that it gets mixed up. And once it is like this, then further if you reduce the separation, then it goes like this. Something of this sort. Something of this sort. Okay, and the actual separation may be somewhere here. Nice pictures you will find in books. Okay, so it will be like this. So the actual separation, actual parameter somewhere here, and if you draw a line, you have states here. So you have, these are the allowed energies. These are allowed energies. These are allowed energies. You have states here, quantum states here, and this is the gap. So this is that Eg, and this is that valence band. This is that valence band, and this is that conduction band. Okay, this is the conduction band. And remember, the total are 8 n states. And here also the total is 8 n states. In the valence band you have 4 n states, and in this conduction band also you have 4 n states. These are states, quantum states, not the electrons. Electrons, you only have 4 n electrons. S2p2 we started with. S2p2 we started with, so 2n plus 2n, 4n electrons. So in lowest energy, in ground state energy, these 4n states will be filled and these 4n states will be empty. So in our usual picture we show like this is your valence band, and then this is the conduction band. This is the band gap, and that's it. This valence band is completely filled at 0K, at very low temperature if you are, and this is completely empty. And this Eg turns out to be 1.12 electron volts at room temperature. This gap is slightly dependent on temperature, but not much. So you can always assume that it is 1.12 electron volts. So this is how it is, the energy band diagram looks like in this one dimension. Okay, 1.12 eV compared with 26 milli electron volt is certainly large, but as I told, it's not very large. It's not 100 times, 200 times like that, and this is enough for this. Is enough for some electrons making transition from here to there and making conduction possible at room temperature.